Yep, we started.
Okay, great. Thank you for joining the Triton community meeting. So my name is Cici. I'm a TPM on the Triton team at Meta. And like I mentioned, Bill's not gonna be able to join since he's on vacation and I'm covering for him. So for today's agenda, we have a couple of presentations from the NVIDIA folks. Looks like we're starting out with the Triton CUDA tile IR backend by mzhu, and looks like he's ready to go. So Feiwen, yes, I think you're still muted. Yeah.
Okay. Thank you, Cici. Hello, everyone. I'm Feiwen from NVIDIA Shanghai. Today, I will introduce Triton CUDA tile backend. And let's introduce the overview first about CUDA tile. CUDA tile actually extended the CUDA programming model to enable the first-class support for the tile program. And then we introduced the CUDA tile IR. CUDA tile IR is MIR-based intermediate representation and compiler infrastructure. And we have CUDA tile IR spec. And in this spec, we define the normal semantics, operation, and type, and for all this tile-based computation. And for this project, Triton 2 tile backend, we want to bridge the Triton language to the CUDA tile IR instead of existing PTEX backend. And we want to extend the Triton compiler ecosystem and also enables comparison and runtime of the GPU kernel written in OpenAI Triton to newly introduced CUDA tile IR backend. And why we raised this project, and CUDA's SIMT program model, because the CUDA SIMT program model extended to operate native on tile-based abstraction, and we want to bridge the Triton with the NVIDIA's next generation CUDA program model, and it can tightly integrate with CUDA stack. For example, the debugging tool and future profiling tool and debugging tool. And this can also offer a seamless path to leverage model hardware compatibility without code rewriting. Because the TIA project, the portable is the first things we will configured, and we also enable the developer to benefit from the Triton's accessible Python syntax while also getting TIA IR native support for the Tensor core and architectural portability. And so I think because the Triton and the CUDA TIA is very alignment. The Triton's approach is Triton is fundamentally a TIA-based programming language, and the developer can just express the computation in terms of block instead of thread. And for the Triton 2 TIA, so we can still preserve the TIA level syntax, and also compare the compilation can direct to the CUDA TIA IR, and no transparent translation to thread level. So we don't using this bridge. So the Triton didn't need to translate to the thread level SIMT code. And you can see the right image, and the left one is the current Triton path. So it needs to translate the tail to the thread for the TIA bridge. So we can just directly, you can see this line, and you can just mapping the to tail, so can just using the TIA backend. And right now the Triton Triton TIR backend, it's easy to adopt. So the existing Triton user, including LM agent, can leverage CUDA TIR advantages without learning new language or writing existing code. And it also very simply to configure. You can just using a virtual environment to switch the backend. You can currently the default backend for the Triton to TIR project. The default backend are still the existing PTEX or current Triton PTEX backend. But if you using a virtual environment, it can switch to the TIR backend. And also the user can select which kernel or which backend he want to use on per kernel belt. So for example, for one program, so some kernel can using the PTEX backend and some kernel can using a TIR backend.
Oh, so this is actually per kernel, so you can annotate the kernel with something to say this is a Triton kernel, but please use this backend instead of that, the other backend?
Yeah. Currently, maybe we didn't, actually we just using the virtual environment to control. So we can add another API to, for example, using API to switch, but right now we're just using a virtual environment to switch for a model. Some kernel using PTEX backend, and some kernel you can using TIR backend.
Okay.
Yeah.
Are you thinking that could be like used by auto-tune to see which one is faster to use which one, or more the user have to know in advance?
Yeah, it definitely can be, but right now we didn't have deliver this infrastructure, but it definitely we can do that.
Hi. So in Triton, so in Qtile, there's a distinction between a kernel and a device function, right? And in Triton, you don't have that distinction. You could instantiate a Triton inject function as a kernel or as a device function. How do you handle that if we are compiling it at a function level?
CUDA, I think this limitation is, you mean the CUDA, NVIDIA CUDA language, right?
Yes, that's right. Yeah.
I think this is only limitation for the CUDA. For this Triton backend, we don't have this limitation.
I see. Okay.
Yeah. And performance tuning tips, and because the tuning space of the TIR backend is totally different from current PTEX backend. That's so for the existing Triton kernel, the user, the developer didn't need to change the kernel, but he have to change the tuning space. And there are three things I need to mention. First is we add a new tuning knob, which called the occupancy. That's to balance the register and the share memory, because the occupancy, this knob doesn't exist in current Triton. And also Triton support the number of warps. This knob is widely used, but for current TIR, we didn't need a number of warp knob, because we found that for the compute bound kernel, we just need to turn in occupancy instead of it's good enough, and we just let the compiler to decide the number of warp. But we just realize.
So if somebody writes some generic piece of Triton kernel and they want to tune the num warps with the auto tuner, what are you going to do?
It can work, but it didn't affect the performance.
It still works,
yeah.
So it will respect that number of warps. I mean, if somebody wants 4 warps or 8 warps, you guarantee that your backend will use exactly what the user asks, or you're going to ignore it?
No, it just ignore. We just ignore. But
isn't that against the semantic of the language?
Actually,
how can you ignore it?
Yeah, but we because it didn't affect, because we didn't expose this number warp knob in
now,
CUDA.
What I'm saying is that if there is an annotation from the user, you can change it. You say you can ignore that annotation. I'm not so sure the language allows you to drop it silently.
Yeah. So internally, actually, in most cases, we internally we set number of warp equal to 4. I forgot it's 4 or 2. So we just using occupancy can generate the same effect and make the same. Just we using for the computer bound kernel, we using occupancy instead of number warp in CUDA 13.1, but in the future CUDA we will still explore this knob. But we realize.
So you're talking about current situation versus what?
Yeah.
Right now it's
because
like that, but then later on it will actually expect the number of warps.
Yeah. Because we just realized for the normalized kernel, for the layer norm, as norm, I think number of warp turning number of warp is still important, and the compiler had to decide choose the best number of warp number. And okay, and the last thing is the TLR didn't need the number of stage knob, but we need a latency knob. So currently we just directly mapping the number of warp to latency. I think they are totally different means, but we just want to make sure the developer didn't need to change the code a lot. So this is 3 things. The turning space, the current TLR turning backend turning space is different from the current Triton.
Are you going to cover how the occupancy is going to be selected by the translator?
I will not cover yet because it's very complicated, because in internal TLR using a automatic warp specialization algorithm. It's a little different from current AWS in the Triton. So it's a very long story.
But is the selection done in the translator or in Triton or where?
We just extend for the occupancy. Did you mean that we just extend the current Triton DSL?
Right.
So
is it exposed to Triton user, or how does it work? Because normal Triton kernel doesn't have occupancy.
Yeah. That's we have to just the user have to rewrite his turning space. He didn't need to rewrite his code, the kernel, but for the turning config, he have to rewrite this part. Yeah. In future, maybe we can deliver some skill to automatically rewrite the config, but right now the user have to, for this part we have to modification the turning, the configure.
I have a couple of questions. First, regarding automatic warp specialization. So in TileIR, is this using the same NVWS passes that are there in Triton, the AREF-based dialect, or is it something different?
It's different. I think the difference is because in TLR's AWS, it's using some cost model, and it have a lot of architecture information and a lot of OCG compiler hint, internal hint. So it's hard to explore to the public. So that make the algorithm is little different from the current Triton, because Triton also have AWS, also contributed by the contribution by the NVIDIA folks, but in AWS algorithm is different.
I see. Another follow-up question. So I've seen the latency optimization hint, compiler hint, and TileIR. What are in Qtile Python? I don't really understand what it is. I mean, what does it correspond to? I mean, is it num stages or?
It's want to resolve the problem, because for the load, it's hard to let the cost model to estimate his latency. For example, a load and then a mass, and if we compiler know the load latency, if it is a static latency, the compiler can schedule the algorithm, the kernel very well. But for a very complex kernel, it's hard to estimate his latency. So we have to explore this to the user or to the alternate to turn the latency, because different latency will decide the software pipeline.
I see. So it's also a fairly wide range, right? Between 1 and 10. So are there any guidelines on how to go about tuning the latency parameter? And I mean, what does it if it's a cost model? I sort of get that it's not easy to reverse engineer it, but I mean, does it like improve TMAs or something like that?
I think for most cases, because I want to, for this page, in practice, we found that only this two knob is very critical, occupancy and the knob CTA. For the latency, for the critical, for the CUDA case, we have to turn the latency. But for most cases, you're just using the default latency. That's okay. We're just using the latency to help the corner case. We found for the corner case, it's that the compiler is hard to decide the software pipeline.
Got it. Thanks.
Yeah. This page introduced for the number warp for the CUDA 0.1. We ignore this knob, but in the future we will add it back. And occupancy is very important, especially for the computer bound kernel. And for the number of CTA, I think it's very critical. We have, because a lot of existing Triton kernel, they didn't turn even if the Triton supports the number of CTA, but the kernel didn't contain this knob. But we found for the TIR, this knob is very critical. And functional performance limitation. And because the project is still in a very early stage, and there are a lot of no issue. For example, a lot of Triton OP we are not compatible with the current Triton OP. For example, I list of the OP we didn't support right now. For example, the TMA gather scatter and dot scaled. And we know that maybe the user experience is not very well in this early stage, but we have planned to support them in the future CUDA version. And also another limitation is TIR actually using an order memory model. So global memory access is not ordered by default. So we in the TIR it have memory token schematics, but because we want to compatible with the Triton, so we have algorithm to translate the ordered memory model to unordered memory model. But there's still some have some corner case. For example, if the memory aliens between different global memory, so the algorithm cannot do this translation. And if the data transaction across different thread box, for example, you're using atomic to do the global synchronization, the algorithm is hard to convert the ordered memory model to unordered memory model, so it may produce some incorrect result. So these two parts we need to improve in the future. And also there are some no performance issue. For example, the small gene performance currently is very poor, and it will be addressed. This problem will be solved in the future CUDA release. And the Tensor point performance, if the kernel still using Tensor point load, and the performance is it's not very good, and it will be, I believe it will address in the CUDA 13.2, and CUDA 13.2 will be released recently. And then also I just mentioned that number of warp is not explored yet in the 13.1.
So would you say at this point, to get good performance from TIR, you would have to write using Tensor Descriptor API, Tensor Descriptor loads, instead of using Tensor of pointers?
API. You can use using Descriptor. Using Descriptor will get performance, but it's only true for the 13.1. But in 13.2, we fixed the problem, and the 13.2 will be released recently. So So maybe the
in the
next
future
you don't need to worry.
you predict that the performance will be equivalent. You don't really need to use tensor descriptor to get good performance. You can also use tensor pointers fine. Even mask loads.
Yeah, I think it's not. Maybe it's the same. Maybe it's very close. It's very close. But because right now the performance is really very bad.
Okay.
Yeah.
We'll see.
Thank you. And also the CUDA TEL roadmap. Currently, the in CUDA 30.1 we only support the Blackwell, and so that's the Triton TEL backend only support the Blackwell chip. But in CUDA 30.2 we will support the Ampere, and CUDA 30.3 we will support Hopper, and in the future new architecture support, and for example, and other feature, for example, the CMT interrupter and the native communication, and a more profiling and debugging tool will support in the future CUDA release. And API compatibility roadmap. Currently, I mentioned that a lot of OP we didn't support right now. But for example, the I mentioned the performance, that the tensor point performance will be fixed in the 30.2, and we will support dot scale and TMA gather scatter and TMA reduce, and the following feature we will support in the 13.3, and in 13. I'm not sure it will. For example, this element-wise inline ASM, it's widely used in current Triton kernel, but we didn't support right now. But we plan to support maybe in the 13.4 or 30.5. And yeah, that's all.
Yeah, a couple of questions. First one is, how like in what scenario, what kind of kernel do you see that using the tile IR backend is better than Triton? Like as a user, how to pick between the two?
Actually, I think for the compute bound, something like multi-head attention, and yeah, that's kind of. But for the normalization kernel, I think current performance is still not good.
Right, I understand current, it's still early on, there's limitation and so on. But long-term wise, is there anything that how IR can perform faster that Triton cannot reach the same performance?
I think eventually, I think they should be the same performance. Okay. Because if we invested more resource, I think just engineer effort.
Okay, and then my second question is, so somewhat related, but now there's a translation from Triton IR to tile IR. Is there anything that CUDA can do that this translation cannot do? Like, is there a benefit of CUDA on top?
Oh, you means the different so the using the CUDA front end versus Triton back front end.
Triton front end, yes. Because the reason of asking this question is like I see a RSC in the inductor that adding a CUDA front end, right? But I was thinking, why not just use the Triton front end, and then if they really want to, someone really want to use CUDA tile IR, they can use this translator to translate to tile IR.
I think it's very hard to answer your question, because if we invested enough engineer effort, I think their performance also should be same.
Okay. And then last question. Is there any consideration or thoughts of doing the other way around translation from like tile IR to Triton IR?
Sorry, can you repeat? So what do you mean?
Because currently the translation is from Triton IR to tile IR. Is there going to be, is there any thought of doing the other way around, tile IR translate back to Triton IR and then use the PTX backend?
I think no. But for the language part, I think it's easily to translate. For the DSL level, I think it's easily to translate. From Triton to CUDA to Triton, I think for DSL. For the I think I don't think we can translate the CUDA to Triton CUDA IR to you means CUDA IR to Triton IR, right?
Right.
Yeah, I don't think so.
I have a related question to the earlier question. So, sorry. Okay, a slightly different question. In tile IR, you've got these view-based loads, right? And Triton essentially follows a pointer-based load. Was there any? What are the implications of the two models being different?
Sorry, I want to repeat you. So your question is why the tensor pointer performance is worse than right now, right?
Not really.
Sorry.
So in Qtile frontend or in tile IR, if you want to target, let's say, TMAs, you express it in terms of views and pass in the tile indices. Whereas in case of Triton, you pass in the actual element offset to the tile, right? So the way it's handled is slightly different, right? Triton looks at it as pointers, while tile IR looks at it as views. And so is there an implication when it comes to translating and from one to another?
Yeah, we have maybe I can't answer your question right now because I maybe didn't catch your. Okay, maybe can you offline send your question? Sorry.
Sure.
Yeah, sorry.
Over chat,
sorry
is it?
Yeah, I have my. I'm not totally understand questions.
So it was essentially that in Triton you treat it as pointer-based loads, right? Even if it's a descriptor.
Yeah.
Whereas in tile IR, it's a view-based load. So instead of the raw pointer, you always specify it in terms of block index. So I thought there was a difference. So is there any implication when it comes to converting it from pointer-based loads to view-based loads, tensor views?
So I'm not sure I can just address your question directly, but for the TIR, for our load, it can internally decide if we are using global load or TMA load.
Okay. Okay, sure. And the question related to the previous question was essentially whether the Qtile front end is expected to be stable over time, or with each new generation should we expect more APIs to come in? I think that might become a challenge if there are more APIs that come into Qtile, and then it might take time for Triton to catch up, right? So is there any? I see that the spec is for tile IR and not for Qtile Python, so I was curious to know about that.
Okay. Yeah, because I think the CUDA tell for the load we can help the user to, for example, we are using the TMA load by default, but if the compiler find that it doesn't meet the TMA requirement, it will fall back to the global load. So we just for the Triton CUDA tell IR, this project we for different to support different front end API, we will do the translate. We have paths to do the translation.
Okay.
Thanks. So just a quick time check. We're 32 minutes into the meeting, and I'd like to give enough time to Rupanshu as well. are we good to go? And if we have time, maybe we can take more questions for Feiwen a little bit later.
Okay, thank you.
Yep, thank you.
Thank you.
Okay, so can everybody see my slides? Okay, so I will get started. Hello, everybody. My name is Rupanshu. I'm a CS PhD student at Stanford. And this work is in collaboration with Rohan Yadav and our wonderful colleagues at Stanford and NVIDIA Research. Please feel free to stop me for questions anytime. You can also put your questions in the chat, and Rohan is here and he should be able to answer them during the presentation as well. Okay. Okay, so as a community, we are in the unfortunate situation where every time a new GPU is released, we must rewrite large parts of our programs. And the rewrites are not mechanical. Often new algorithmic advances are needed to achieve peak performance on new GPUs. I'm going to pick on the flash attention series of kernels for this talk. So the Hopper GPU was announced in March 2022, and then it took over a year, I think almost 2 years, for flash attention to be customized for peak performance on Hopper. And then the same thing for Blackwell, where it took over a year for flash attention to be customized again for peak performance on Blackwell, which wasted countless flops in the interim. But if you actually look at what changed between flash tension 2 and flash tension 3, the main difference was a new software pipeline and warp specialization strategy. And then again, from 3 to 4, there was another new pipelining and warp specialization strategy. So why were our compilers unable to find flash tension 3 and 4 automatically? If the main thing was just a compiler transformation, why couldn't we do this automatically? So I would argue that the crux of the matter is that the combination of these two optimizations is poorly understood. Software pipelining is well understood, and we have known optimal algorithms for software pipelining since the 1980s. But warp specialization is much less understood. Only heuristics are known for warp specialization. And then their combination is not understood well at all. So today I will tell you how to solve the problem of pipelining and warp specialization optimally. And before I describe our solution, I should say there is industry interest in solving this problem. The PyTorch Triton team, I believe some of these people may be here today, put out this blog post recently where they identify doing this sort of global joint optimization across scheduling and synchronization as one of their future goals. So our approach relies on the intuition that pipelining and warp specialization done together is really a resource-constrained scheduling problem, where the goal is to schedule the program to run at maximum throughput, subject to various constraints of the hardware, such as throughput of the Tensor core, how many registers a watt can access, what is your shared memory capacity, and so on. And as we go on, I will try to explain that the problems of pipelining and warp specialization must be solved jointly. It's just like pipelining decisions deeply interact with decisions about warp specialization. And the only way to obtain schedules that achieve peak performance on our GPUs is to solve these two problems in a joint manner. Okay, so our approach is called TWIL. So let's see how, I'll give you an outline of how it works. So we take a program written in some high-level DSL, such as Triton. In the first phase, we are going to do optimal software pipelining. And this is really trying to ask the question of what is the highest throughput this program can achieve on some GPU. And this is really a maximization problem, right? You're trying to maximize throughput. In the second phase, we try to find an actual pipeline and warp specialization schedule that actually achieves this throughput. And this then becomes a satisfaction problem. And the output of TWIL is a software pipelined program with warp annotations. By warp annotations, I mean every instruction is annotated with the warps it's supposed to execute on. And these warp annotations can be processed by a lower level compiler pass to generate executable code. But this output completely gives the pipelining and warp specialization schedule. Okay, so I want to.
I have a question, Rupanshu.
Yeah.
So the specialization is at the warp level, right, and not at the warp group level.
Well, we can do both. We can like when we do warp specialization, we know that some things have to be in a warp group, and so that is one of our. You can add that constraint.
Okay. The reason I asked that was because as I understand, one of the advantages of warp specialization is that you can have a different register allocation at the warp group level, but I don't think that is applicable at the warp level, right? So is that typically a performance hindrance if you're splitting it at the level of warps? Do they still not end up using the same registers?
Well, you can make different decisions about register allocation in a warp and also in a warp group. I mean, eventually the decision is like how many registers a warp can use. We can find all those decisions. Like I will explain later in the talk that like there is no limitation of the system where like by considering warp or warp groups, you can miss some schedules. Does that answer that?
Okay. So I thought the set max and reg PTX instruction was at the warp group level. But as I understand, you can control registers at the warp level. Is it? Or,
this is the warp level, I think.
No. Okay. So yeah. Set max and reg is warp group level, right? But I mean, what Rupanshu will show is that I mean the formulation doesn't really matter if you're talking about warps or warp groups. Like you can just say certain operations need a warp group to run, and like that's all you need to tell the system. It's kind of unrelated to the core problem that we're solving. You know exactly how many warps are needed to run any particular instruction. This is just kind of parameter of the input.
Okay, got it.
Okay. So in the first phase, we're going to do optimal software pipelining. So let's see how this works. So I won't go into too much detail about software pipelining for this talk, but just to recap quickly, software pipelining is an instruction scheduling algorithm, and where it exploits instruction level parallelism to within and across loop iterations to improve throughput. So if you have some program like this, where like every box gives an instruction, software pipelining would generate something like this, where the stream of instructions has been compacted by virtue of instruction level parallelism to increase throughput. And the code looks something like this, where you have for loop on the left hand side, and then if you apply software pipelining, you get sort of a for loop, but with a prologue and an epilogue before and after it. And the idea is that this new loop will have faster throughput. Okay. But in TWIL, the algorithm we use for computing a software pipeline is called modulo scheduling. And again, I won't go into detail about how modulo scheduling works for this audience, but it is a de facto standard approach to software pipelining today. However, we rely on an optimal modulo scheduling algorithm, which guarantees that it will find a software pipeline with the maximum throughput for a program on a given model of the GPU. So like once you run this algorithm, you know what is the best possible throughput you can get for a program on a GPU, and there's nothing better you can do. And the algorithm we use is adapted from this paper. We adapt this algorithm for GPUs. Okay. So let's look at the second phase. In the first phase, we try to find the maximum throughput. Now our job is to find an actual software pipeline and warp specialization strategy that achieves this throughput. So to do this, it is critical to have a theory of warp specialization. We need to understand exactly when is warp specialization of a program helpful. Okay. So, a Hopper SM has 2 to the 16 registers. If your program only has a single warp, most of these registers are unused because a warp can only address about 2 to the 13 registers. What that means is if you add an extra warp to your program, well, then you can access more registers. Up to a point, of course. So this is one resource that warp specialization gives you. If you add more warps, in some cases, you can get access to more registers. The other resource that is given by warp specialization is an instruction stream, because warps have their own instruction streams, and they can issue instructions independently of each other. When can this be helpful? So consider this situation. Here I show 3 instructions all running on the same warp. The problem is that the blocking wait that is required to read the result of the gem interrupts instruction issue for the exp. And this causes a loss in performance. How do we fix this problem? Well, we can just put the exponent on a separate warp. Because warps have their own independent instruction streams, a blocking wait on one warp cannot impact instruction issue on a separate warp. So this is another example where warp specialization actually helps the program. Okay, so the last example is about variable latency instructions. So we're doing software pipelining, and software pipelining is fundamentally a static instruction scheduling algorithm, which means that you must have a fixed latency for every instruction in your program. And this information is easily available for most instructions we care about. Here I give some example numbers. These are not real. But what latency do I assign to TMA loads? The latency of a TMA load fundamentally depends on whether it gets a hit or miss in L2 cache. And this cannot be predicted statically. So how do we do software pipeline in the presence of these instructions for which a fixed static estimate of the latency is unavailable? So our approach is that we assume we put all variable latency instructions like TMA loads on a separate warp and let them run ahead of the rest of the pipeline. And so by doing so, we ensure that outputs of TMA loads are available by the time they are needed by the main pipeline. And then if this is true, then their latency can be assumed to be 0 from the perspective of the main pipeline.
Is that true? Because if you have a lot of loads, you're going to start to saturate the cache and get eviction in the cache. So I'm not sure. How can you predict that all the slots will be available exactly when you issue the gem? The result of the lot is available when you, because you consider the lot to have 0 latency.
Mm-hmm. Yeah, so this is not a guarantee, and the pipeline will not be so sometimes it will you can get very unlucky and you can get a lot of misses in L2 cache, and then it might not actually be 0. But this is fine for our purposes, because
okay, so
in
you
some
say
sense,
most of the time, other than pathological cases or big programs like that, then this is actually true. Yeah, I agree with that statement.
Yeah. And in a sense, this is what people already do, and it's very hard to come up with, because we're doing static instruction scheduling fundamentally. And so if you give me an instruction for which I don't know a static estimate of the latency, this problem is very hard. It's very hard to do anything. But we found that this approach, which is applicable only to a limited set of programs, seems to work well for our GPUs. And I'll show you some performance results where this actually
is this for a sorry for interrupting. Is this for a fixed tile size or chunk of data that you that you load, or is that also a variable?
Yeah, so we have a cost model, and the cost model will look at the size of the data you're loading and the size of the gem you're doing, and it will give a clock cycle latency.
Okay. Is that based on arithmetic intensity, or
it is based on throughput numbers. We look at what the throughput is of the Tensor core on Hopper or Blackwell, and then that throughput number can be converted into a clock cycle number. Basically. Okay.
Yeah, just to be clear, all the operations here are in Triton IR, all the tiles have some fixed and known size at compile time, right? So you know that you're doing a 128 by 128 by 128 gem. So you then go look at the table and compute your cycle count, etc.
Okay. So I try to give you a theory of warp specialization. So hopefully we understand why we want to add warp specialization to a program. But how do we actually do it? How do we operationalize this theory? So what our approach is that we take like an initial software pipeline program generated in phase 1 by our optimal software pipelining algorithm. And then I'm going to use this program to define an SMT problem. Okay, because as I alluded to earlier, this step of finding an actual schedule that achieves the given throughput, this is really a satisfaction problem. So we're going to use SMT solvers to do this. So the solver really works over this table. And the solver's job is to sort of fill out this table. And once you fill out a table, it gives you like a concrete pipelining and warp specialization schedule. And so what the solver is doing is that it's like placing instructions into this table, and it has a bunch of constraints that placement of instructions must satisfy. And so it tries to find a satisfying assignment of adding all the instructions to this table. And once it finds that, like that is guaranteed to be like an optimal throughput pipeline and warp specialization strategy for your program. Okay. So I'm going to give you some examples of actual SMT constraints that we use. So first of all, the table is represented inside the solver as a Boolean array of a four-dimensional Boolean array. It's called op. It just has like the same dimensions as the columns of the table. And so this Boolean variable is true if like the row corresponding to instruction v, instance I, clock cycle t, and warp w exists in the table. Okay, so if this row exists in the previous table, then this variable is true. This is what the solver thinks about. Okay, so now our job is to write down constraints that define what it means to be a valid schedule. Here's our first constraint. So we're doing static scheduling because we're solving the joint problem. So we need to care about latencies. So this constraint says that the exp needs at least 80 clock cycles to execute. So how you read this constraint is like on the left-hand side, it says, if you issue the exp at time t on some warp, then like gem, which is the consumer of the exp, cannot be issued until time t prime, where t prime is less than equal to t plus 80. Right. So if you stare at this for a few seconds, you can convince yourself this is exactly like encoding the natural language intuition about it. So this is one constraint that we use. There are more complicated constraints. For example, here, this is the constraint for checking that the size of live data on a warp does not exceed its register budget. Okay, and there are like interdependencies between these two. Like this, the array live in the second constraint is defined in terms of the array op. And so it's like this complicated dance of constraints that the solver does. And this is very hard to reason about for humans, but you just write these constraints down, and our SMT solvers are able to find a satisfying assignment. Okay. If you want to see the full set of constraints, they're in a preprint. Okay, I want to show you some actual results. So we ran TWIL on a high-level implementation of flash tension. So we took like the Triton DSL implementation of flash tension. And from that code, TWIL is able to derive the flash tension 3 schedule. This graph only shows the warp specialization, but we also derive the pipelining that we do. So this is like almost exactly the ping pong schedule that humans found by hand. And this is derived completely without using any heuristics, such as producer or consumer warps. Okay, this is just SMT constraints doing their thing. It can also do flash tension 4. Okay, so the same program, you just pass a different flag to TWIL saying, I want you to do this for Blackwell. The same user level program can be used to derive a different schedule for Blackwell. And this is exactly like the flash tension 4 schedule that people have found by hand. And this is much more complicated. Like if you were relying on producer, consumer, warp special, that kind of model, you would not be able to come up with this warp specialization schedule. But because we're using FMT constraints, the solver just naturally comes up with this. Okay, I want to say a few things about the implementation. So Twill is implemented as a bunch of Triton compiler passes. So we take Triton GPU IR and we emit Triton GPU IR with warp annotations. We try to get the rest of the Triton compiler to like lower our code to executable code, but we couldn't convince it to like lower it to performant code. And so to convince you that these schedules are real, we did what we call hand compilation. So we took the Triton GPU IR produced by Twill, and we translated each line to CUDA C++ by hand. So we wrote like this kind of code where like in the comments, I give the IR instruction that I'm translating, and below that is like the C++ code that implements that IR instruction. So we did this by hand. We also considered translating to Gluon, but we ultimately decided on C++ because like at the time, Gluon was not achieving maximum performance on these kernels, and we just thought we wanted full control. We did C++. Okay, so here is our results for Hopper. And so we're running out of time, so I will just quickly say Twill is on par with the expert Flash Tension 3 implementation on Hopper, which is much faster than Triton. And then on Blackwell, Twill is again almost on par with cuDNN and Flash Tension 4, and much faster than Triton as well.
These numbers are also collected around in December or so. So in case Triton has improved since then, we wouldn't have grabbed those improvements.
And here I give the wall clock times for Twill to find the Flash Tension 3 and 4 schedules. This time includes both phase 1 and phase 2. And most of this time is spent in the SMT solver. So I want to say something about how tools like Twill can be used. Clearly, like Twill is much slower than what would be required in the fast path of a compiler meant for interactive development. But I would say that optimal schedules can guide the development of fast heuristics for a compiler. Like as a compiler writer, it's really difficult to come up with good heuristics if you do not know what the optimal schedule looks like. And also, is there a question? No? Okay. And also, like if you're just writing kernels by hand, or like your agent is writing kernels, it's really helpful to have as reference an optimal schedule so that you don't have to look at a given schedule and sort of stare at it to convince yourself whether there's something better that's possible. So this is my last slide. Twill is a developer tool for doing optimal pipelining and warp specialization on our modern Tensor Core GPUs. The main idea in Twill is you decompose the problem into two phases. In the first phase, you use an optimal sorter pipelining algorithm to compute the highest throughput achievable. And then in the second phase, you use an SMT solver to find an actual schedule that achieves this throughput. So our preprint is available if you want to check it out. Happy to take any questions. Thanks for listening. Yes.
Is the code open source? I mean, is it there in the Triton repository?
Code is not open source yet. It's at NVIDIA. We're trying to open source it.
Okay. Yeah, I'd love to like take a look at it.
Yeah.
Another related. I mean, okay, not a related question. So does this actually fit into the polyhedral model? Because I mean, I'm sort of aware that there again you try to solve an ILP problem, and typically the loops that you try to pipeline are affine. So would this sort of like fit into that? Can you like sort of do fusions and all that all at once?
It is a good question of what the relationship of this is with polyhedral methods. I haven't thought about this, so I mean, like I can't give you a good answer off the top because I've never thought about this connection. I mean, I think they're pretty different. We're not doing fusion. We're just doing like scheduling, right? So there's no like the operator fusion or anything happening here. That's one thing I'll say.
Yeah, I'll say also I don't know if it's directly related to polyhedral analysis, especially because like, I mean, for most software pipelining algorithms, you start with assuming maybe the dependencies between all your instructions are known. Like maybe you could use polyhedral analysis in a more complicated program to figure out those dependencies, but And especially for these kind of tau-based programs, like polyhedral analysis is not required to do such a thing.
Okay. Yes.
Would it make sense to like use this as a kind of like more automatic tool during development? So kind of like with Helium auto tuning, right? Where your developers are expected to like run the auto tuner once instead of every time when compiling. Like, could we run this, produce annotations, and then like stick them next to the kernel somehow in a way that's not intrusive? Like, what kind of abstraction or interface would be needed to plug this schedule that Twill generates maybe once into the kernel, so that then like when the kernel gets compiled for different architectures and so on, it could get used every time? Or I guess it's architecture dependent also, right?
Yeah, I mean the way we implemented it is that Twill outputs Triton IR with every instruction is annotated with the warp Twill wants you to execute it on, right? And so we try to integrate this with like the Triton AREF infrastructure, which does accept this kind of code. There's a way to say on every IR like what it should be on, and we tried integrating Twill with this, but it turns out that like the rest of the compiler was not able to generate performant code. So this is the kind of interface I'm imagining, where like we just like sort of pipeline the IR for you, and then for every instruction I tell you what warps I wanted to be on, and so this can be consumed by lower level tools.
Yeah, an alternative is also, I know like Triton Meta's TLX extensions had the ability to kind of group instructions into tasks and then say that different warps would run those tasks. Like you can imagine taking the output Rupanshu said and like you then go and annotate your program with tasks. Though I think we did find that that most Triton compilers are bad at still accepting software pipelined IR and lowering the software pipelined IR well. So that might be harder to tell tools what to do.
So why were you not able to generate TTGIR based on the schedule you found?
So we generated TTGIR, but the problem was this TTGIR was not able to be lowered by the rest of the Triton compiler into performant code. Like we ran into issues like, the compiler could not figure out how to allocate tmem correctly, which is not something that Twill tells you how to do. There were also like performance issues where I remember an issue where like, it would serialize all the WGMMA, so you were losing the overlap.
I mean, but you control those things, right? In TTGIR, you control kind of the TMM allocations. You control the WGMMA. What part of like the compiler would be blocking you?
So I think for the WGMMAs, we generated like the best code that was possible in TTGIR, but I remember a case where it was lowered by like the NVIDIA specific backend, where it had some heuristics for figuring out where to add weights or something, but like the heuristic was going wrong, and it was adding the weight immediately after the WGMA, so you were not getting any overlap. And we tried to like tinker with this a bit. Like we tried to add weights on our own and then sort of see what like if it worked, but like it was just not. Code was not being lowered correctly. But like performance.
And I think also, Thomas, I mean, it's just our goal also was to kind of do this exploration of software pipelining and warp specialization. I mean, we're not experts in like the remainder of the Triton stack below it, and felt that after, I don't know, a month of debugging this, we thought it was more productive for us to kind of write the kernels in C++ than figure out, the right ways to make Triton do the lowering correctly.
Right. I guess I'm trying to understand. So, like, are you saying that you were trying to get the existing pipeliner and warp specialization code to do the transformation for you, like, and you are not trying to actually like generate the TTGIR on your own? Because I guess the part I'm trying to understand is
so
there should be very little logic after that. Like below, like the TTGIR, there's actually very few choices the compiler make.
So one important choice the compiler has to make is it has to add like the AREF thing. Like you have to add like the output
but that's much earlier, right? That's like before. So that AREF stuff is like if you like before the warp specialization. I guess so I think you answered my question saying like you were trying to instrument before the warp specialization and pipeliner in Triton, and you did not try to instead just
we were getting
those
rid of Triton's warp specializer and pipeliner, right? Like we did our own and then handed that IR to passive after the warp specializer and the pipeliner.
But then there's no more ARF or anything like that, right? ARF only exists in the warp specialization pass.
No, I mean, what Rohan is trying to say is that like in the output of TWIL, I like add annotations, and the annotations are like supposed to guide the generation of ARFs, right? Like the ARF pass is supposed to look at like, okay, this instruction is on this warp, the consumer of this is on some other warp, so I have to add a channel to communicate it. Like this part was not lowering our code correctly. Like we were hitting like compiler bugs, like it was just like asserts were failing, stuff like that.
Okay, yeah. So you were trying to use the warp specialization pass. I mean, at least the bottom part of the warp specialization part.
Yeah, the bottom part
of
yes.
Triton.
Yeah.
Which, I mean, I guess it's not very surprising to me that it won't accept any like random schedule. But I'm curious here if it would be interesting to see if it's possible to like instead make like your own kind of like have the pass like take this I got a pass that takes the schedule and automatically generate I guess directly the TTGR code.
Yeah, I would love if that existed. Like that would have helped us a lot because like we have this whole thing where we do like we solve like expensive NP hard problems and we like tell you what the best schedule is. I just want the rest of the compiler to like faithfully lower that.
Right. Yeah, I guess so. I mean, on the pipeliner side, it should be very few choices in like so we do work like that. Also, of course, there's few corner like being cut, but where like you can annotate every single instruction with like the stage and the order of them, and the pipeliner should make almost no choices. But yeah, on the warp specialization part, it's not quite as decoupled.
Yeah.
I think, Luca, you have your hand up, but I don't know if you've gotten a chance to speak yet.
Oh, yeah, sorry. My questions were mostly answered. Yes, thank you.
Cool.
Thank you.
Do we have more questions? No. Oh, a bunch of people just dropped. Looks like that's a wrap for today. Well, thank you guys for presenting.
Thank you.
Yeah, I see there's some question about.
Yeah, I dropped our emails in the chat. I don't think that was on Rupanshu's slide in case anyone has any more questions. We're happy to discuss.
Okay. Yeah, I will also be posting information about GTC, the Triton events we're going to have during GTC in the GPU mode Discord group. So if you want to look there, if you want to reach out to us. All right. I think that'll be it today. Thank you guys for joining.
Thank you.